So when you're studying calculus, usually you start finding derivatives of trigonometric functions at the very beginning. Usually courses follow this early transcendental rule, but one obstacle that you run into when you try and do that is using the definition of derivative to find limits that involve expressions such as these. So the limits of sine of a function, sine of x divided by x, for example, is something that will show up frequently. And I think it's important to understand this not only for those applications involving derivatives, but to be able to solve for limits as well. So I wanted to show how to compute this first limit. So a proof first of why this is actually true, why this limit equals to 1. So you can plug x values that are closer and closer to 0, such as 0.1, 0.01, 0.001, or even negative 0.1, and so on, to convince yourself that this fraction sine x over x approaches 1 as we go on. But to actually get a proof of this is not very easy. So let me show you what my proof of this is. I've seen this proof somewhere before, and this is the proof I've used so far since then. So what I start doing is I draw a unit circle. This is my best unit circle. And then I draw the angle x. That's my angle x. As you know, the radius of the unit circle is 1, which is why it's called the unit circle. And then a geometric proof, so I'll change colors because I'll draw 3 different triangles on this. And then with this 3 triangles, I'll squeeze this limit in between 2 lengths. So actually the second one is not a triangle, you see that. You will see that in a second. So my first triangle is this blue one. What I know about this triangle is that it has hypotenuse 1, and this vertical side here, if I call it y, right? It'll be true that sine of x is the opposite over the hypotenuse. So the sine of x equal to y. So that means that vertical length I drew actually measures sine x. So just be clear, this measures sine x. So that's the first thing that I draw. The second thing, and I'll change colors again, is not really a triangle, it's a circular sector. So a portion of a circle, like a pizza slice, right? So what do I know about this? I want to look into this length right here. In this drawing, in the unit circle, any angle is usually measured in radians. And, let's think about in terms of proportionality. If x were the entire angle, the entire 2 pi, then the length of this, right? If the angle were 2 pi, then you would get a 2 pi r as the circumference, right? But because the angle is x, then you get an xr. So that's a proportion argument, right? 2 pi is to 2 pi r, just as x is to xr. So the length of this is x because r is 1, right? The radius of the unit circle is 1. So this is x right there. This length is x. Now the last drawing I'll make, and that's going to be a purple, it's another triangle. Now it's the big triangle here. Touch that line there. They all have to have the angle x, so they all are going to be sort of inside the other like that. So now what do I have? If I call this last outer value y, I know that the tangent of x, looking at this purple triangle only, is the opposite over the adjacent. So it's y over 1. So y is the tangent of x. So this vertical length is actually tangent of x. Okay, so how does that help me? So let me go back to blue. What I can see then, sorry, let me do this slowly. This is the bigger of the three lengths, this is in the middle, and this is the shorter of the three lengths. Okay, so that means the tangent of x, right, is the biggest, the sine of x is the smallest, and then x is in the middle. Okay, so that is what I have. Okay. All right, so how does that help me? Let me expand that now. So the sine of x is less than x, which is less than sine x over cosine x, we know that. If you divide all three sides by the sine of x, we get that 1 is less than x over the sine of x, which is less than 1 over cosine of x. And now we can do a squeezed limit theorem argument. So the limit of 1, right, if you go on the left side first, and let me go back to doing my blue and purple colors there. So let me go and say that the limit of 1 when x goes to 0 is a constant, so it's just 1. And the purple side, which is this, is the limit of 1 over cosine x when x goes to 0 is just 1 over the cosine of 0. The cosine of 0 is 1, so this is also 1. So we have a function in the middle that's between these two, and both limits equal 1, so the middle function has no choice than to also equal 1. That's by the squeeze limit theorem. Right? Remember this idea, right, of the squeeze theorem. You have, two functions at 0. You have the function 1 there, and you have the function 1 over cosine, whatever it is. So I don't know, something like this. They both meet at 1. The green function, which is this, right, the middle one, I don't know how it behaves, but I do know that whatever it does, it's got to stay in between the two. So even if it tries to escape somewhere, it's got no choice but to stay between the two and go to 1. So that's the idea. This is the reciprocal of what I wanted, but it's the same because the limit of sine x over x when x goes to 0 is the same as the limit when x goes to 0 of 1 over, right? It's the reciprocal of x over sine x. And by the quotient rule, or the quotient law for limits, this is the limit of 1 divided by the limit of the bottom, the limit of the top divided by the limit of the bottom. As long as the limit of the bottom is not 0, we can do that. So this is then 1 over 1, which is 1. And that is my proof. This is so important that we call this the fundamental trigonometric limit. And I hope this proof was enough to convince you.